We're going to talk about conical pendulums, and a good starting point is to look at what a conical pendulum looks like when it's just an object hanging by a string. And if we analyze the forces, one thing we need to note is that we've got two forces interacting here. We've got the force weight, otherwise known as the force of gravity, which equals mg, and we've got the force tension, Ft. And if this thing's not moving, it's just sitting there, the tension in the string is equal to the weight. You can plainly see that the tension is equal to the weight of whatever this object's mass is. As this thing starts spinning around, tension is due to a string, so the tension starts taking on two-dimensional properties, okay, where force tension's here, okay, but the weight is still directed down towards the center of the earth, so force weight is still directed downward. Okay, so it's no longer the case that the force tension is equal to the force weight. In fact, force tension has a component in what we would define as the x direction, pointed inward. Force tension in the x direction that's pointed inward, and it has some component of force tension in the y direction. Now, those are some of the forces that are acting, and the center-seeking force is defined as the tension in the x direction. That's the center-seeking force, or the centripetal force in the case of the conical pendulum. A couple of other things that we can note are, or dimension at least, are the length of the string that the conical pendulum is attached to, and its association with the uh, the height. And the height's going to change depending on how fast you're spinning this conical pendulum. If you spin it faster, it's going to start going up higher, and the radius will increase, and the height will decrease as you spin this faster and faster. But if we just take it at a certain given point in time, there's going to be some sort of radius of the circle that the conical pendulum is circulating around, and there's going to be some dimension of height. And you can see that the triangle that's made with the conical pendulum with a given angle theta here. And let's just relabel some of these things in terms of what we're used to. This is Ft, force tension, right here, force tension. Okay, directward, upward. This is our force weight, mg. Force weight is equal to mass times gravity. And we have a radius. And again, as shown in the slide before, this tension has x and y and x components. Some of the things we can do with this conical pendulum is we can take everything we've kind of learned in the past and what we've recently learned about circular motion, and we can derive an equation for the speed of the conical pendulum. And we're going to put this in terms of its radius, r, its radius, lowercase r, and its angle, theta, the angle theta. So we're going to derive a simplified equation for solving for the velocity. And when we're deriving these equations, we want to start with, our net force equation. Okay, start with the net force equation, and we know that the net force of anything is equal to the mass times the acceleration that that force causes. Okay, and if we're talking specifically about, we want to know the speed of the conical pendulum, well then we're interested in the centripetal force and the associated centripetal acceleration. And we can note that the centripetal force is actually made up of one single force, and that is the tension in the x direction. That is the center-seeking force. So that is the only center-seeking force, or force that's uh, associated within this uh, plane. Uh, so that is what our net force is in the centripetal direction, for lack of a better term. So this is actually force tension in the x direction. And that force tension in the x direction is equal to mass times acceleration. Mass times centripetal acceleration. And centripetal acceleration we know is equal to, v velocity squared over the radius. Is equal to the velocity squared over the radius. Now, we need to know a couple of things here. We need to know what the force tension is in the x direction. We need to derive what the force tension is in the x direction. And we can see that if this is our angle theta, okay, if this is our angle theta, then we have a triangle here for the force tension x, y, and the magnitude of the force tension vector makes a triangle where the angle theta is right in here. So let's redraw that and see visually what I'm talking about. So we've taken our vectors and the components and we've made a triangle out of it just to clarify what we're talking about. And we want to know what force tension is equal to. And we want to derive an equation. We want to put it into terms of uh, theta. Okay, so we want to get theta in our equation somehow. Uh, and we also want to take our x and y components and we want to put it in terms of tension. Or, if possible, mass and gravity. Because those are quantities that we can readily explain or measure or, is a constant. So, what we have here is the same as every other time that we've broken vectors into components or vice versa, where we've taken the components and turned it into a vector. We have a triangle with an angle. Now this angle theta is the force tension is the opposite side of that angle, and the tension in the y direction is the adjacent side. And if we remember our SOHCAHTOA rules, we can see that in this case, which is a little different than what we're used to, but the force tension in the x direction is equal to the magnitude of our vector, or the hypotenuse, times the sine of theta. And the reason why it's sine is because sine of theta is equal to opposite over hypotenuse. Okay, so if I would bring this over to the other side, I'd have to divide both sides. So sine of theta is equal to opposite over hypotenuse. In this case, the opposite is the x component, which tells us that the force tension in the y is going to be using force tension times cosine theta. One other thing we can note as we look at this picture is the only forces acting in the y direction on the object that is spinning are the force tension in the y direction and the force weight. So essentially, these two forces are equal. So force tension in the y direction is equal to my force weight, which is mass times gravity. So that's going to benefit us as we derive this equation for speed also. And we'll see how it does that in a few seconds. One thing we can do is we can take force tension in the x and substitute in what that is equal to in terms of force tension and theta, because force tension x is equal to force tension times sine of theta. So this part of this steps down to become this because force tension in the x is equal to ft sine theta. Now we want to put ft into terms of theta as well, and we can do that. We can do that by dividing both sides by cosine of theta. But before we do that, we want to get rid of our fty, and we want to put in something that's measurable. And here you go. What can substitute in for fty? Mg, mass times gravity, is equal to fty. So you can get mg over here is equal to our force tension times cosine theta. And if we divided both sides by cosine of theta, we'd learn that force tension is equal to mg divided by cosine of theta. So we can take all of this and plug it in for our force tension. That leads us to a further expanded equation. Mg cosine of theta times sine of theta equals mv squared over r. And again, we're going to try and derive the equation for velocity in terms of the radius and the angle theta. And we can see that, hopefully you can see that we have a sine theta over cosine theta. That reduces down to tangent theta. If you're unsure about why that is, you can look that up. You can ask me in class, but that is equal to sine theta over cosine theta is equal to tangent theta. And you should also be able to see that our masses here are going to cancel out. So mass cancels out. We're left with, and these cancel it out to make tangent theta. So we're left with g. If we multiplied both sides by the r, we'd have radius times gravity times tangent theta equals v squared. So to derive an equation in terms of radius and theta, we got to take the square root of both sides to get our velocity equals the square root of gravity times the radius times tangent of theta. This will work to find the velocity of a conical pendulum if you have the radius and the angle that it is spinning around the circle at. And we already know what g is. We know that's 9.81, so that's a constant. We'd only have to measure those two things. If you can't measure the radius, maybe you can measure the length. That's simple enough. You can measure the length of something and then figure out the radius through trigonometry because you have the angle. or vice versa. You could figure out the angle if you had the length and you had the height that it's spinning around at. There's a number of ways you can measure this triangle out to get theta or any of the other properties, any of the other linear properties, uh, in order to utilize it to solve for the velocity.